In this lecture, we want to look at modeling of assembled processes. Assembled process is one in which the output and the input are assembled. We want to determine the relationship between the assembled output and the assembled input when we are given the transfer function of the process in the Laplace domain. In other words, we want to determine the Z transfer function of the process when we are given its transfer function in the Laplace domain. The input to the process is a sequence of numbers. Therefore, it can be expressed as a summation of weighted impulses at the respective sampling instance. The summation can be expanded into the expression shown. Now, the inverse Laplace transform of the TF is equivalent to the impulse response of the system. Since the system is linear and the input is a summation of impulses, the output is equal to a summation of impulse responses to the respective input impulses. The output at sampling instant k is given by the expression shown. We have substituted for t in the continuous output expression using kt. The Z transform of the input is given by uz equals a summation for n equals 0 to infinity of unt by z to the minus n. Let's define Gz as the Z transform of the impulse response. In other words, Gz is a summation for n equals 0 to infinity of gnt by z to the minus n. Let's find the product of Gz and uz. After some mathematical manipulations using the expressions for Gz and uz, we get an expression that is equal to the Z transform of the sampled input. Therefore, Gz uz equals yz. So, we can regard Gz as the Z transform block of the sampled process. And that's a diagram to illustrate yz is the sampled output, uz is the sampled input, Gz is the Z transform block of the process. Gz is equal to the Z transform of gt, which is equivalent to the Z transform of the inverse Laplace transform of Gs. To get Gz, we can follow these three steps. Step number 1, we determine the inverse Laplace transform of Gs to get Gt. Step number 2, we replace T with Kt in the expression for Gt to get the sequence Gkt. Step number 3, we determine the Z transform of the sequence Gkt to get Gz. In practice, we can skip step number 2 and obtain Gz directly from Gt using Z transform tables. In this example, we are given Gs as being equal to 1 over s plus 1. We want to get Gz. The first thing that we do is to get the inverse Laplace transform of Gs, and we obtain it as Gt equals 1 minus e to the minus t. We substitute for t using Kt to get the sequence Gkt, and the expression that defines the sequence is 1 minus e to the minus kt. To get the values in the sequence, we can substitute in that expression using different values of k from 0 up to infinity. The third step is to determine the Z transform of the sequence Gkt. The result will be gz, and the expression for gz that we obtain is z1 minus e to the minus t all over z minus 1, z minus e to the minus t. Then alternatively, we can obtain our gz directly from the TF. So we partialize gs to get the partial fractions 1 over s and 1 over s plus 1. Then we refer to the tables to get the corresponding z transforms for those partial fractions. We sum them up and we obtain gz. We notice that the two answers are the same. In digital control systems, the process is preceded with a DAC. The purpose of the DAC is to convert the discrete signal from the controller into a continuous signal that will in turn be input into the process. The TF of the process is denoted as GPS. The TF of the DAC, which is a zero order Holt DAC, is denoted as G0S. We want to determine the relationship between the sampled output YK and the sampled input UK. We notice that the ZOH and the process are in cascade. Therefore, their overall TF is G0S GPS. Let's replace G0S with the actual TF value. We get our overall TF as 1 minus e to the minus ts over s by GPS. To obtain GZ, we use the methods that we have already used to convert a Laplace transfer function into a Z transfer function. We obtain the expression shown. Let's separate the term that contains an exponential from the term that does not contain an exponential. After that, let's find the Z transforms for the respective terms. And after that, let's factor out the common term in the results so that we obtain a compact expression. We will get the expression for GZ as GZ equals Z minus 1 over Z by the Z transform of GPS over S. So this is the general expression that can be used to obtain the Z transfer function for a process preceded with a ZOH. In this example, we are given GPS as being equal to 1 over S plus 1, and we are told that it is preceded by a zero order Holt. We want to find GZ. We substitute for GPS in the general expression using the value of TF given in our example. We obtain the expression for GPS over S as 1 over S by S plus 1. We then apply the necessary steps to obtain the Z transform of that expression. After combining the results, we will get our GZ as being equal to 1 minus e to the minus t over Z minus e to the minus t. The TF of a process GPS with a time lag of nt seconds, where n is an integer, is expressed as e to the minus nts by GPS. Let's apply the method for obtaining Z transfer functions from Laplace transfer functions to this case. We obtain GZ as being equal to Z minus 1 over Z to the n plus 1 by the Z transform of GPS over S. This is the general expression that can be used to obtain the Z transfer function for a process with a time lag. In this example, we are given GPS as being equal to 3e to the minus 2s over s plus 1, and we are told it is preceded by a zero order hold. Sampling period is 1 second. We want to find Gz. We notice that the TF represents a process with a time lag. By inspection, we note that NT equals 2. Since T equals 1, this means that N equals 2. Then the process TF that we are going to work with is 3 over S plus 1. We substitute these into the general expression for finding Gz. We get our Gz as being equal to 1.896 over Z squared by Z minus 0.368. Let's look at block diagram rules. We will begin with the block diagram for a sampled process. We have already derived the relationship between the output and the input of a sampled process, and we expressed it using Z transforms. From that relationship, we get the corresponding Z domain block diagram as a Z transform block Gz with input Uz and output Yz. Uz is the Z transform of the sampled input. Yz is the Z transform of the sampled output. For cascaded processes, we first obtain the overall Laplace TF of the cascaded processes before we obtain the equivalent Z transfer function. Therefore, using an example with the two cascaded processes, the Z domain block diagram for the process is a Z transform block G1, G2, Z. The notation G1, G2, Z is used to show that we first obtain the overall TF G1, G2 in Laplace domain before we convert it into the Z transfer function. For cascaded samplers, each process is independently converted into an equivalent Z transfer function. Therefore, in the Z domain, cascaded samplers are essentially cascaded blocks. Using an example with the two cascaded samplers, the equivalent Z domain block diagram is the Z transform block G1Z, G2Z. The notation G1Z, G2Z is used to show that we obtain the Z transfer functions of the processes independently. Please note the difference in notation between cascaded samplers and cascaded processes. Let's look at the diagram for a closed loop digital control system. We want to determine the TF for the closed loop system. We observe that the process and the zero order hold form two cascaded processes whose equivalent Z transfer function is Gz. The algorithm is discrete. Therefore, the algorithm and Gz form two cascaded samplers. Let's analyze the signals in the diagram. Please note that whenever a signal is a star, it means that the signal is sampled. Let's begin by obtaining the expression for the output ys. After that, we obtain the expression for the sampled output y star s. We convert it into the z domain and we obtain the expression yz equals g0 gp z dz ez. We then go on to obtain the expression for error relative to the other signals. After that, we obtain the expression for the sampled error. We then convert it into the z domain and we obtain the expression ez equals rz minus g0 gphz dz ez. In the expression for error, let's make ez to be the subject of the formula. We obtain the expression ez equals 1 over 1 plus dz g0 gphz rz. Let's substitute for ez into the expression for the output. We obtain the expression yz equals dz gz over 1 plus dz g0 gphz rz. Therefore, the closed loop TF is fz equals yz over rz, which is equal to dz gz over 1 plus dz g0 gphz. If the system has a unit feedback, hs will be equal to 1. Therefore, the closed loop TF will be equal to dz gz over 1 plus dz gz. I recommend that you attempt these questions from chapter 6 before you proceed to the next lecture.